My name is David Pridmore, and I'm excited today to present to you Reducing Furnace Operating Cost. IGBT technology saves energy. I'm presenting to you today from Roman Manufacturing, located in Grand Rapids, Michigan. We specialize in water-cooled transformers with a customized transformer list of over 8,000 different models. We also specialize in component and system sales. We have developed a new technology, IGBT MFDC, for the furnace industry to provide more electrically efficient furnaces. So what is IGBT MFDC technology? IGBT stands for Insulated Gate Bipolar Transistor. MFDC stands for Mid-Frequency Direct Current. You can think of IGBT as the component, whereas MFDC is the overall technology. This technology replaces SCR and VRT controls. And in this presentation, we will show you that IGBT MFDC has several benefits, including balanced three-phase input, inductive shielding, and precision power control. In order to understand the benefits of MFDC technology, we must first understand the limitations of VRT and SCR technology. VRT stands for Variable Reactance Transformer. A variable reactance transformer typically uses three-phase input with a DC choke and a reactor to control voltage output. The typical problems with the VRTs is that they are large and bulky, have major power factor deficiencies, a lagging response time, and often must be matched to the load. SCRs, or silicon-controlled rectifier, also have limitations. SCRs control voltage by decreasing the on-time of a natural sine wave. They typically use a single-phase input, which is inherently unbalanced, and those imbalances are reflected back to the power company. SCRs and VRTs both control voltage by reducing the on-time of a 60 Hz sine wave. This reduced on-time creates inherent inefficiencies in the powering of a furnace. Let's look at a typical program for a furnace. As a furnace is in a ramp phase, the control is providing 100% power. And with a VRT or SCR control, this means full sine wave. However, the time a furnace spends in ramp phase is relatively short. The soak phase is a period of time where the furnace is simply maintaining a temperature. During this phase, the voltage is scaled back anywhere between 30 and 60% of full sine wave. You can see on these waveforms that there is a considerable amount of off time. This off time introduces inefficiencies into the system, and inefficiencies cost money. Herein we define the problem. Power is expensive. As the cost of electrical energy continues to rise, manufacturers are looking for ways to reduce power consumption, or the energy lost in transmission. Today, furnace customers have dedicated systems to keep their power use under control, and this control is going to keep on getting tighter. We at Roman Manufacturing are excited to introduce a new player to the game, the IGBT MFDC solution. An IGBT MFDC system is an inverter control that creates 1000 Hz output coupled with a DC transformer connected to the furnace. Let's look at each component of the system closely. We start out with a balanced three-phase input. A note here states 480 volts. However, other standard voltages can be used. This three-phase input is then rectified onto a DC bridge. This bridge and capacitor acts as a shield from inductive loads and imbalances on the heating element side. Rectified three-phase 480 volts is converted to single-phase 650 volts. This introduces the concept of high-efficiency, high-voltage power transmission. We then use an IGBT to rapidly turn on and off high current at 1000 Hz. This high frequency allows us to create smaller transformers. A transformer then produces the high current necessary to heat the furnace. A key portion of our value proposition is this high voltage transmission. When we rectify three-phase up front, we start with a higher voltage. That higher voltage allows us to step down the necessary voltage at a higher ratio. This correlates to lower current draw and lower peak demand. We then rectify the transformer output to direct current. As I will cover later in this presentation, direct current is inherently more efficient on many levels. To start, let's look at a typical furnace circuit. A typical furnace circuit is comprised of a control, a transformer, and a heating element. As we developed our IGBT MFDC technology, we looked closely at each of these stages of power use. We examined power consumption upstream, i.e. what the power company sees. We measured the power between the control and the transformer, which is usually high voltage, low current. And then we looked at the power between the transformer and the heating element, typically low voltage, high current. In order to understand our value proposition, I want to go into detail about the cost and loss of power at each of these steps. A power bill from a utility company has 5 aspects of cost. The first is real power, or usable electricity. This is measured in kilowatts. Reactive power, or wasted electricity, is measured in kVA, reactive, or kVAR. kVAR can be created by inductance and other disturbances in the electrical system. Finally, there's the total power, or apparent power. This is measured in kVA. The power triangle here shows reactive power and real power 90 degrees out of phase. They are summed up vectorially to give us total kVA. The angle this triangle forms, or theta, is our displacement power factor. Peak demand is the highest usage charge. This is the ability to use more power than is normal in an operation. During the development of IGBT MFDC, we sat down with major power companies and asked them, what exactly makes power expensive? The answer? Furnace customers get charged for kilowatts and are penalized for low displacement power factor. So what is displacement power factor? Displacement power factor, as I described earlier, is the angle between the real and reactive losses in a circuit. Essentially, it is how the current leads or lags from the applied voltage. The leading or lagging of current creates an unnecessary burden on the power company and makes electricity more expensive. This is where I'm excited about IGBT MFDC technology. With SCR and VRT controls, more off time correlates to lower displacement power factor. However, with our IGBT MFDC technology, the displacement power factor stays close to unity at practically any set point. In summary, our goal is to help you save money on energy. Anywhere energy is lost in transmission to the process creates an opportunity for us to save energy. Roman Manufacturing has been committed to this approach for many years. The development of smaller water-cooled transformers enables us to move closer to the process, which greatly reduces power consumption and overall material cost. The IGBT MFDC system is the next step in our evolution towards energy conservation. In order to demonstrate these savings, we will evaluate individual components in an IGBT MFDC circuit in order to better sum up where losses occur. The source of power losses in an AC electrical system can be attributed to overall impedance. Similar to the power triangle, the impedance triangle here shows resistance and reactance 90 degrees out of phase. Resistance generates usable power output, whereas reactance generates lost power output. In a system with a fixed resistance, heat output is primarily dependent upon current, as shown here with Joule's law. In an ideal system, we want the only resistance in the circuit to generate heat in the furnace. Any unnecessary resistance or reactance creates power losses. When we reduce impedance, we get more power for less cost. Let's examine how we can do this. Resistance is a relatively simple concept. Resistance comes from the sum total of components, including cables, busbar, jumpers, and load. Ohm's law tells us that a larger circuit will require more voltage for the same amount of current. Efforts taken to reduce resistance outside of the heating element will allow us to drive more current at a lower voltage. This is a consideration when designing busbar dimensions and material types. Additionally, Roman's smaller water-cooled transformers allow us to get closer to the process and thereby reduce resistance. This correlates to lower voltages, less transformer, and cost savings. Reactance is the lost power equivalent in the impedance triangle. Reactance is a result of alternating current and is a function of both the area of the circuit as well as the frequency of the waveform. From the equation here, you can see that as area and frequency increase, the reactance also increases. It is important to note that reactance is derived from the magnitude of changing current. Therefore, the high current secondary of a transformer has an exaggerated impact on the reactance losses in a system. One way to combat these losses is through close coupling of transformers to a process. However, with IGBT MFDC technology, direct current has no frequency, and these exaggerated secondary losses are eliminated. Let's examine why a DC output is truly better. With a standard model, we will apply 480 volts to a transformer primary. This voltage can be stepped down to 10 volts, and you can see we have a low current primary and a high current secondary. At the transformer primary, an induced voltage is generated, which opposes the applied voltage. This induced voltage is a function of the magnitude of current change and has a relatively low impact because we have low current. Therefore, our usable voltage remains relatively high. However, with the low voltage secondary, the induced voltage, which is a function of the higher current, creates a higher opposing voltage. This is why high amperage alternating current in a transformer secondary exaggerates reactance losses. The impact of reactance on the usable voltage of a secondary is exaggerated and should be avoided. With IGBT MFDC system, we rectify the transformer output directly to direct current and eliminate these losses. We actually measured these losses in a furnace application. We measured the reactance voltage drop in the secondary cables of a 3-transformer furnace system. The length of cables from the transformer to the furnace was only 6 feet. By measuring AC and DC resistance, we determined that 0.4 volts were lost in each circuit due to reactance. Each heating element was conducting 787 amps, giving us a total of 0.3 kilowatts per circuit. With 3 circuits per furnace, we have a total loss of 0.94 kilowatts in each furnace. These losses add up over time, and with longer secondary cables, you can expect to see even more dramatic losses. With our IGBT MFDC technology, this loss is completely avoidable. In summary, impedance can be thought of as the overall AC resistance of a system. Ohm's law tells us that if we can reduce overall impedance of the system, we will need less voltage to drive the same amount of current. This means smaller, less expensive transformers and less power usage. Additionally, the angle formed in the impedance triangle is the same angle in the power triangle, which is the displacement power factor. Lower displacement power factor means higher penalty from the power company. Now let's get into why IGBT MFDC technology truly is superior. As demonstrated earlier, the IGBT MFDC system takes 3-phase input. It rectifies it to a high voltage DC bus. We then use IGBTs to invert the DC to high frequency, high voltage, high efficiency, alternating current. A transformer then produces the high current necessary for furnace heating, which is then immediately rectified into direct current. This output is then connected to the load. IGBT MFDC technology has been used in other markets since 1990. There are multiple forms of communication available. IGBT MFDC is balanced across 3 phases. Any avoidable or unfavorable inductance in the load will be shielded within the control. The displacement power factor remains near unity at all practical operating ranges. The high frequency output of the inverter allows us to use smaller transformers. The direct current output mitigates reactance and also produces more efficient heating. The best part is that all of these benefits are present at typical operating ranges, unlike with SCR and VRT controls. There are very few drawbacks of the system. We do require a 3-phase input. There are also some additional losses across the control. However, the power gains outweigh the loss overall. I want to take a moment here to describe the difference between DC and AC heating. Direct current heating is inherently more efficient. I previously described Joule's law, which is a function of current, resistance, and time. With SCR and VRT controls, there is a considerable amount of off time. During this off time, the heating element is not being heated. With IGBT MFDC controls, we do not decrease off time, we just decrease the average current. With a continuous application of heat, there is no quench phase as there is with SCR and VRT controls. Additionally, alternating current creates vibration in the heating element and furnace components. With IGBT MFDC technology, there is no vibration. Now let's get into some experimental data. We performed a head-to-head comparison of IGBT MFDC to an SCR control. As a controlled variable, we matched the secondary currents and used the exact same secondary load. We then measured upstream power consumption for the same amount of power output. In the picture here, you can see the two transformers side by side. The blue transformer is the standard AC transformer connected to an SCR. Below it, you can see the much smaller MFDC transformer. You can imagine how these size differences can add up in your facility. At the bottom, you can see the 3 set points that we took measurements at. We took measurements of 100% full sine wave, 70% of full sine wave, and 40% of full sine wave. Here are the results. You can see that we have lower power consumption across the board at commonly used set points. This means that if your furnace is in a soak phase at a set point of 40%, you have 45% less kilowatt consumption, 75% better displacement power factor, and 60% less kVA. We may not be as efficient at 100%, but furnaces don't spend a lot of time here. How is this possible? DC heating with high voltage, high efficiency power delivery is inherently better. VRTs were not included in this comparison, but are estimated to behave similarly to SCR controls. In conclusion, SCRs and VRTs have inherent electrical and inefficiencies in their typical operating ranges. The reactance from AC heating is an unnecessary additional load and cost to the system. The off time from a chopped sine wave reduces heating effectiveness, and displacement power factor is very low at commonly used set points. With IGBT MFDC technology, however, this has mitigated these unnecessary losses in the system by minimizing reactive losses. A rectified high voltage primary means more turns per transformer, which leads to lower peak demand. And displacement power factor with IGBT MFDC is close to unity at most set points. The cost savings with our new IGBT MFDC system are not only limited to the furnace, as you could realize savings with upstream equipment such as breakers, feed wires, and distribution transformers. Thank you very much for your time. I'm now open for any questions.